Okay, hello everyone. I have the pleasure to introduce Daphne Stam. It's our today's colloquium speaker, and I'm particularly pleased, Daphne, that you made time to speak to us, not only because of your of the superb topic you're representing, but also of the inspiration you always provide. So Daphne is an associate professor in planetary science at the Technical University in Delft, and as many of us know, Delft is the hotspot for aerospace engineering. So people make a note in your ears for those. Daphne has done her PhD at the Vrije Universiteit in Amsterdam with ÖAW-Institut. And I don't know, ÖAW stood for polarimetry in astrophysics. So therefore, there's kind of a earmark here. Yeah. Daphne held various postdoc positions at the Anton Pannekoek Institute in Amsterdam, at ESRON, of course, then at the TU Delft, also at Cornell University, and returned with one of the prestigious NWO grants called VIDI to ESRON, right? And ESRON, she led the planetary, or from this position in ESRON, she led the planetary group of the EPS division, which must have been a substantial amount of work. I will leave it to Daphne to, of course, explain her research focuses, but I would like to quote two of those. So one of her research focuses is on numerical modeling of flux and polarimetric signals and of course also of the interpretation for solar system planets and exoplanets. And this is how she is known and connected to various people here on this call. But Daphne does also instrument development, and in particular, she developed the spectro-polarimeters for planetary observations. And here I'm just rattling down, Daphne, I hope you forgive me, a couple of those instruments, because I think this is where it very nicely links to the interest and the potential of this institute. So Daphne has initiated the design of SPECS, and SPECS stands for spectro-polarimeter for planetary explorations. And the point here is it is very small and very robust, which made it a perfect candidate for ExoMars, and it eventually flew as payload on ESA's L-class tandem to Titan, and also on the Venus M-class mission. Let's see what else I have. Yes, and of course, SPECS, an adaptation of the SPECS design made it onto JUICE, unsurprisingly, and I'm really happy to hear that, or to have learned this.
No, that's not that true. No.
No? Oh, no. Okay, you could.
No, so SPECS was proposed for ExoMars, but actually it only exists on paper at the time.
Okay, at the time for ExoMars, yeah. Mm-hmm.
So ESA said, no, it cannot fly, but we want to have it on another mission. And so they wanted to have it on JUICE. Mm-hmm. But then we got a new director in the institute, and he said, no, we know everything about solar system planets.
Oh, that's amazing.
Okay,
then I misunderstood this.
Yeah.
Okay.
So he gave SPECS to Earth observation, and it will actually be launched on an Earth observation mission.
Oh, cool. Yeah. Okay, very nice, very nice. And then I dropped two more abbreviations. These are LOOP and SELFIE, and I think I really like SELFIE. Maybe you say a few words about this at some point. Yeah. All right. I think I'm closing this introduction by saying again, Daphne, I'm super pleased that you made time to talk to us today. And if you're ready, please take the screen.
Yeah, thanks for introducing me. So I'll share. We already tested it. Should work.
Yes, we see the beetle.
Yes, this is a dung beetle. And so dung beetles are very special. Well, they can make these very nice spheres of dung, but they can also see polarization. So they can do something that we cannot do. Well, I don't know. I've never tried to make a sphere of dung. But so with their tiny eyes, they can see the degree, so the vibrational direction of the light waves of the sky. And they use that to walk. So you can see the head is over here. So by following the pattern on the sky, they can walk along a straight line. So that is very special of these beetles. So we cannot see polarization with our eyes. Well, there is a very tiny region in our eyes that is sensitive to polarization, but you really have to know how to use it, where on the sky, in order to see a slight yellowish spot of light in the sky. So we cannot really see polarization. So maybe that's the reason that the polarization is not very often studied. And so with this talk, I hope that you get interested in polarization, like a dung beetle. So polarimetry is a tool for characterizing planets and exoplanets. And this is a picture of actually of the Earth. So what is polarization? So light waves have usually, photons have the vibrational direction of the electric field and the magnetic field. Light waves that arrive at a planet from the sun, they have arbitrary directions when you integrate it over the sphere of the disk of the sun. And so we call that light unpolarized. But when this unpolarized light hits a planet, it is scattered by the gas molecules, by the cloud particles, the aerosol particles. It is reflected by the surface. And all these reflection and scattering processes polarize the light. So the light that is reflected by a planet or an asteroid or a moon, of course, is usually polarized. So the light waves have a preferential vibrational direction. And so the degree of polarization of that light, we usually call P. That is the ratio of the polarized flux over the total flux. So if P is 1, then the reflected light is completely polarized. All the light waves have the same vibrational direction. If P is 0, then the directions are arbitrary, like the incident sunlight. So this degree of polarization is very interesting because it is very sensitive to the illumination and the viewing angles of a planet, or of course of a part of a planet, not the whole planet, but also part of a planet. It is also very sensitive to the properties of the atmosphere and the surface. So to, for example, the size of cloud particles, their composition, and also their shape, and the roughness of the surface. And so this all ends up in the degree of polarization. And because these properties, their interaction with the light waves depends on the sizes of the particles, P is also very sensitive to the wavelength of the light. It is also insensitive to a lot of things. Well, for example, because it's a ratio, the degree of polarization of a planet is insensitive to the size of the planet or to the distance between the observer and the planet. So that's very nice, because if you don't know that very precisely, well, the degree of polarization is insensitive to it anyway. It is also insensitive to the total flux of the incoming light, because it's this ratio. And it is also insensitive to many instrumental effects. Well, that depends on your instrument, but if you have a detector that is degrading in time, then this degradation is usually the same for the polarized flux and for the total flux. And so the degree of polarization stays the same. When I talk about the degree of polarization, I refer mostly to the linearly polarized light. And that is because the circular polarized light, where the light waves, the direction of the electric field rotates, that degree of polarization is usually very small. It is negligible compared to linear polarization. It is very interesting, circular polarization, especially if you want to search for life, because of the homochirality of biological molecules. Light that is scattered by biological molecules is usually circularly polarized. And because circular polarization is very hard to get just from random scatterings in the sky, you can potentially use this to find life. The problem is that the circularly polarized flux is always extremely low compared to the total flux. So the degree of circular polarization will be maybe 10 to the minus 3 or 4. So it's very hard to measure, but it is interesting. So Here I have a classic example of what you can do with polarimetry. So this is actually a very old example by Jim Hansen and ÖAW-Institut. So they took observations of the degree of polarization of Venus, disk integrated, so Venus as one speck of light. And these observations were at different wavelengths, 3 wavelengths, and also at a range of phase angles. So the phase angle is basically how much of the object is illuminated. So when you see the planet like this, then the phase angle is 0 degrees. Half a planet is 90 degrees, and then the night side of the planet is 180 degrees phase angle. Of course, at 180 degrees, Venus would be exactly in front of the sun. And at exactly 0 degrees, Venus would be behind the sun, seen from the Earth. So these phase angles are not in the plot. But all the little dots here are measurements by various people. So not by Hansen and Hovenier themselves. Over a long time with different instruments. And here are 2 plots for different wavelengths. This is 0.55 microns and this is 0.99 microns. And so they did model calculations to find out which type of cloud particles could actually fit the data. And so they found out that particles with an effective radius of slightly more than 1 micron and a very narrow size distribution, so all the particles have basically the same size, and they should be made of 75% sulfuric acid. Those particles fit the observations. And so in this plot on the left, the other curves are for particles that have different sizes. So for example, 1.2 microns is the dotted line here. And 1.5 microns is this very high line over here. But it's very sensitive to the size of the particles. And then on the plot on the right, there is the refractive index. So 1.43 was the index that fitted best. Before this analysis, people did not know what the clouds of Venus were made of, because by just observing the total flux, even at lots of wavelengths, even at lots of phase angles, does not give you this information. You can fit water clouds to the flux. You can fit lots of different clouds to flux measurements. So this polarization really gives you information that you cannot get in a different way. Here is a more recent observation of the polarization of Venus. So this is an observation where Venus is actually spatially resolved. These observations were with the William Herschel telescope with an experimental polarimeter from the group of Christoph Keller, who used to be in Leiden, but he just moved to Flagstaff actually. So yeah, but this is from his group. And so on the left, you can see the total flux. So this Venus over here. This is the subsolar point, North Pole over here. And then on the right, you can see the degree of polarization across the disk. These observations were done by someone who did not aim to observe Venus. So Michiel Rodenhuis was at a telescope waiting for the sky to get dark, and he emailed me, "Oh, I see Venus in the sky. Do you want me to do some observations?" And then he measured all these weird rings on the planet. Very narrow rings. And we can actually explain these rings. We have looked for a very long time for an explanation, because we have only, well, this measurement at a few wavelengths, but not on other days. And these rings can be explained by a density wave above the clouds. So then the planet heats up here near the subsolar point, and the density waves of the gas, they ripple to the backside. And then you can actually, with very tiny density waves, you can get these types of ring patterns. So yeah, but these density waves are invisible in the total flux, but in the polarization, you suddenly see interesting things. So unfortunately, on that day, well, the sky was extremely clear. And unfortunate is that we could not repeat these measurements, partly because it was an experimental polarimeter that was broken down before Michiel actually discovered these rings in the data. And also we tried a few times later, but then the weather was never that good. So also because Venus is usually low in the sky, and then you have hazes. So yeah. In one set of measurements, we have a hint of this. So, and we know that there are waves in Venus's atmosphere. This is something, well, that maybe gets a future. So the main reason for all these patterns in polarization is that the degree of polarization, the dependence as a function of the phase angle, is very insensitive to multiple scattered light. So light enters a planetary atmosphere. Part of the light is reflected back to space after just a single scattering. This light leaves a very strong polarization signature that depends on the particle properties. But of course, part of the light will go deeper in the atmosphere and get scattered a lot of times. And that will also be reflected back to space. But the interesting thing is that this multiple scattered light is usually mostly unpolarized. So it lowers the degree of polarization of the reflected light, but it does not change these interesting regions, for example, where the degree of polarization of the single scattered light is 0, or where there is a peak or a dip in the degree of polarization. So these features remain even when you add unpolarized light. And so, for example, this is a computation for a completely cloudy planet with thick clouds, also completely integrated over the planet. And then you have, for example, 4 sample particles that could go into this cloud. And so the particle that I put in the cloud is particle C, and the other particles have the same refractive index with slightly different sizes. And so you can see that this dip here is here. The peak is still there, but in the single scattering, it is 50%. And here it is, well, maybe 7%. And you can see, so the 0 point is still there, and the 0 points over here are still there. So the shape remains the same. It just gets a bit flattened. And of course, in the planet, there's also gas on top of the cloud. So that also changes a little bit the signature. So this is why polarization is so powerful, that you can still see the single scattering properties, even if you have a lot of multiple scattered light. And in the flux, this is washed out, these signatures. Also nice is that when you are at the Earth's surface and you observe through the Earth's atmosphere, the degree of polarization is insensitive to absorption in the Earth's atmosphere. You might end up with fewer photons, but the degree of polarization is the same. There are also disadvantages, and one of the disadvantages is this 0 polarization and 0 phase angle, and also on the night side of the planet. So this is a disadvantage because if you are on the Earth or in orbit around the Earth and you observe the outer planets, you will only observe them at small phase angles. And so the degree of polarization of the outer planets is always very small, seen from the Earth. So this might also have decreased the popularity of polarization. So here you can see Earth-based polarimetry of Jupiter by McLean et al. And so here you can see in different bands, U filter B, V, and R, Jupiter. So you can recognize Jupiter, but the degrees of polarization are quite low actually. And so what you can see, for example, here you can see the red spot that has a different degree of polarization. You can also see the poles because there is a polar haze on Jupiter, and these polar haze particles are very fractal-like and much smaller than the cloud particles, and so that's why the polarization is very different there. You can see the bands, not in all the wavelengths. In the long wavelengths, they basically disappear, and that is because the band structure, you can see it in polarization because the bands are, you have the belts and the zones, and I always forget which one is lower and higher in the atmosphere. The belts, for example, are low in the atmosphere and the zones are higher. And so the belts have more gas on top of them, and that changes their polarization signature. So that's why at the short wavelengths, The gas scatters very efficiently. That's why you can see these belts and zones at a shorter wavelength. This is a shadow of a moon actually. And this red area, well, that might be an ice cloud below the red spot. So this is a picture. That could be this region. That should be this region over here. But we actually don't know yet why this polarization here is very different. It's not, this polarization is not inside the red spot. So it's not inside this area. It's over here below. Yes, but the degree of polarization is very small, and preferably you want to have different phase angles, not just one phase angle, because the phase angles combined gives you the information. So from the Earth, the inner planets, so especially Venus, of course, can be observed at all phase angles. So that is ideal for polarimetry. The outer planets are less ideal because the phase angle is always small. So if you want to do polarimetry of an outer planet, you should go to space. You should go in orbit. So that's why we want to have specs on views, but it's not there. So you want to be in orbit, but there have been quite a lot of polarimeters in orbit. So the pioneers had some polarimetry, so not a lot, just 1 or 2 bands. The Pioneer Venus orbiter, Voyager's a Mars 5 lander of the Russians, the Galileo orbiter around Jupiter had a polarimeter, although they did not use it a lot because something got stuck and they managed to unstuck it again, and so they did not want to try it again. The Huygens lander had some polarimetry. Cassini had a polarimeter. Venus Express did not have an official polarimeter, but it had this PICAF instrument that has 2 channels in it for acousto-optical observations, and these channels were sensitive for different polarization directions, and they actually downloaded the channels separately. So there was some polarimetry in there, but it was not calibrated. ENVISION, so that is the new M-class mission of ESA to Venus, and it might have polarization. We are still discussing that. The PI, Anne-Karin van Dalen from Vira, is in favor. So yeah, hopefully in the next weeks, because they have a filter wheel with 1 empty spot, and maybe we can put in 1 polarimeter, or maybe they want to redesign the filter wheel with slightly more spots, and then we have full polarimetry. And India is also working on a Venus orbiter, and that might also have polarimeter, but that will be a Venus Express type. That is not the ideal polarimeter that you would want to have on a mission. So it has been used a lot, but you have to go to space to really get all the advantages for the outer planets. But then for exoplanets, of course, there are new possibilities. Because if you are on Earth or in orbit around Earth or close to the Earth, you can see an exoplanet at a range of phase angles, depending on the orientation of the orbit. So if the orbit is face on, then you only have 90 degrees, which is actually a good angle if you have to choose an angle for polarimetry, 1 angle. But if the planet is more in an edge-on orbit, yeah, it will go through different phase angles. And so you can capture the polarization at a range of phase angles, which is precisely what gives you the information about the clouds and the surface. Yeah, so with the rise of the exoplanets, interest in polarimetry has actually increased. Also, that is something completely different. So you can use polarization for characterizing a planet, but it also helps to actually detect the photons of a planet, because the photons of the star will be unpolarized, and the photons of the planet, in the visible near infrared, they will be polarized. So using polarization helps you to increase the contrast between the two. And especially the stellar photons are a huge problem if you want to do direct imaging of exoplanets. Yeah, so you can use it for just finding the planets, and then if you can actually measure the polarization, you can use it for characterization. Of course, yeah, you all know there are more than 5,000 exoplanets nowadays that have been confirmed. lots of exoplanets, different methods have been used to find them. There are not that many direct imaging planets yet, so planets that have been found by actually taking a picture basically of them, but that will increase, and there are plans, of course, for huge space observatories like Habex, LUVOIR, to do direct imaging of exoplanets. Because, of course, we know very little about these planets. This is just a nice impression of the TRAPPIST-1 planets swarming around their star. Of course, James Webb will target TRAPPIST-1 with transit spectroscopy. But with transit spectroscopy, you probe the outer part of the atmosphere. You do not probe the lower parts, not the clouds actually, and also not the surface. So to do that, to do the whole atmosphere and the surface, you need direct imaging. And here is an artist's impression of what these planets might look like. Of course, with comparison of the terrestrial planets in the solar system. So they might actually be very interesting. They might have oceans. This planet is probably locked, so there's a subsolar ocean with ice maybe on the edges. This one is a bit warmer with less ice. So they might be very interesting and very diverse. So what do we want to know about all these planets? The atmospheric composition, the structure of the atmosphere, where are the clouds, how many clouds are there, the temperature, and also of the clouds, of course, the composition and the thermal phase. Are these liquid particles, icy particles? We also want to know the surface composition. Is there an ocean especially? Are there only desert-like areas like this on this artist's impression of Proxima Centauri b? We want to know the rotational period, the obliquity. Are there any seasons on the planets? Are there moons, tides? Is there a magnetic field? Is there plate tectonics? And of course, are they habitable or potentially habitable? And a very important thing is, of course, is there liquid water? Because liquid water is essential for life as we know it. So that's what we want to know. And and with direct imaging using the ELT, for example, or a huge space observatory with star shades like this one, we hope to get imaging light, starlight that is reflected by a planet. So that will be from the UV to the near infrared. And this will usually be linearly polarized. Or, of course, the thermal radiation that is emitted by the planet at longer wavelengths. This can be a little bit polarized because thermal radiation that is emitted will also be scattered in the atmosphere, and then it will get polarized. Except that it will usually be very isotropic, so the signal will be quite low. Unless you have really patchy clouds in a very special pattern on the planet, then the degree of polarization with thermal radiation might be measurable, but it is expected to be very low. And polarimetry is indeed considered. Well, there is already the SPHERE instrument on the VLT that has a simple polarimetric channel. They have actually detected a planet in polarization because it is quite a big planet with a dusty disk around it with SPHERE. The Gemini planet imager also has polarimetry, but really for detecting and also for doing disks, because polarization is also something you can use for disks. They have not detected a planet as far as I know, but that was also not their goal. For the extremely large telescope, there is an instrument, not first generation, that's called EPIX, the Earth-like Planet Imaging Camera System, that will have a polarimeter. The Nancy Roman Space Telescope, that will actually have a polarimeter, so that will be built also partly at ESROM. So you'll be able to do polarimetry. And for these huge space observatories like LUVOIR and Habex, of course, we also try to get polarization on them. And it is actually mentioned in the decadal review of NASA to have this polarization for detection, especially of oceans. So we are getting there. So here are some model computations to show you what a Jupiter-like exoplanet signal might look like. So this is disk integrated, so not spatially resolved from the planet, and from the UV to the near infrared. And these curves on the left are total fluxes, and on the right there are polarization direction, degree of polarization, for 3 different Jupiter-like planets. So for a planet with only gas, that's the black line, the low line over here, and the high line over here. A planet with gas and a very thick cloud in the atmosphere, that is the blue line over here, and the middle line over here is the blue line. And then the same planet with the gas and the cloud and a thin haze on top. Now in the flux here, that is the purple line, very close to the cloudy line. And then here on the degree of polarization, you can see that the haze line is different from the cloud line. So this is haze plus cloud is different from the cloud line. So this is at a phase angle of 90 degrees. For exoplanet, this is actually an angle that you expect to be able to observe, because independent of the inclination angle, this phase angle happens at least twice in an orbit. And the planet is also far away from the star at this phase angle. So you can see, well, the flux just decreases. There are absorption lines by methane. This is all methane absorption. And when you have cloud or cloud with haze, the flux is higher outside the absorption bands because the cloud is very reflective. The haze is thin, so it does not really change the flux a lot. So in the polarization, in the blue wavelength, there's mostly scattering by the gas because it is very efficient in the blue. So the degree of polarization will be about 30%. For the completely gas planet, it will increase because you get less multiple scattering, so more single scattering that has a higher degree of polarization. The cloud particles usually have a somewhat lower degree of polarization than the gas, so that decreases the polarization. And in this case, the haze adds more multiple scattering and also a slightly different direction of polarization, and so in total it lowers the degree of polarization. You can also see the absorption bands. So in the flux, well, absorption just removes flux, so there are these dips, and the depth depends on where the clouds basically cut off the methane absorption bands. In the polarization is usually higher when you have absorption. Again, because absorption removes multiple scattered light mostly, and so you have a higher fraction of single scattered light that has usually a high degree of polarization. So that's why the degree of polarization goes up very high, but you have very few photons, of course. That's something to keep in mind. With the haze particles are high in the atmosphere, and so when you have absorption, a large fraction of the light in the absorption bands will be scattered by the haze particles because they are above most of the absorption. And the degree of polarization is then determined by that of the haze particles. And here that is actually not very high. So that also changes the degree of polarization in the bands. So this is what you could look for when you try to observe an exoplanet. And this is an example of measurements. So what does it really look like? And these are measurements of the Earth, because the polarimeters that have been in space do not have they usually have one broadband observation, not a high spectral resolution. And so these measurements were done from the roof of Astron when I worked there, looking up, looking at the zenith for different solar zenith angles. There were no clouds, so the sky was completely clear. And this is the solar zenith angle. So this is a low sun, and this is a somewhat higher sun. And so what you can see is, as a function of the wavelength, well, first the curves are at different altitudes. That's because of the scattering angle. A low sun, and you look at the zenith, then the light has a scattering angle close to 90 degrees. That gives you a higher polarization. And then you see a lot of spectral structures. And well, absorption bands, oxygen, water vapor, ozone over here. Well, very few photons, so the noise was very high here, so we had to cut it off. So this increase is basically due to the decrease of the multiple scattering. There is also this decrease here. That is the reflection by the surface, because you have light that is reflected by the surface up into the atmosphere and then back to our telescope and instrument. So this is the red edge of the vegetation, basically. And there are lots of lines over here, and they are due to rotation or Raman scattering by gas molecules. That's an entirely different scattering process, also interesting. But so there's lots of structure. And here are some model computations for Earth-like exoplanets with a less detailed spectral resolution. I'll not go into the details. This is for different cloud coverages, but you can see the same absorption bands. This goes to 1 micron. The measurements did go to about 800 nanometers. So you can see the same structures appearing. So this is what an Earth-like exoplanet might look like, depending on the cloud cover and the surface coverage. And what is very interesting application of polarization is actually finding the composition of the clouds. And Theodora Karolidi, who is now in Florida at university, she did computations to show that if a planet has water clouds, then well, in the flux here at different wavelengths, you do not see a lot of special things happening as a function of the phase angle. But in the polarization, you have this peak over here at about 40 degrees phase angle, and that is a rainbow. So that is light, sunlight, that is scattered in cloud particles. So this rainbow is very polarized, and that is something that is at this position, this phase angle, is unique for water cloud particles, liquid water clouds. And so by doing exoplanet observations around a phase angle of 40 degrees, well, you want to cover an area, and if you find this peak, then that is a very strong indication that the clouds are made of liquid water. So for Venus, you do not see this peak. And also if the planet is not completely cloudy, because this is computed for a realistic Earth, and also if there are ice clouds mixed with the water clouds, you will still see this rainbow. So these are model computations. This has not actually been measured because there is not an instrument in space that can measure this. Yeah. So what people, so these are actually not some more computations of the ocean and clouds. What you can see here is what the reflection of light in the ocean, how that changes the polarization. And what is special of the ocean is that you have this glint pattern. So this very strong reflection of the sunlight or the starlight in case of an exoplanet in the water. Of course, you cannot resolve the planet. You have one speck of light. So this glint pattern will be, well, it will be averaged over the disk. But a former master student of mine, Victor Trace, did computations for ocean planets with waves, so different wind speeds, because the wind speed changes the width of the glint pattern. If there's no wind, if the ocean is completely flat, the glint will be extremely narrow, like a delta function. But if you have a lot of wind, you will have waves and you will have a very broad glint pattern. And in these computations, he did for different wavelengths. So the purplish is in the blue, in the UV, and the brown is the longest wavelength. For different Earth, with the same wind speed, so the same glint pattern, with different cloud coverages. So this is a planet with 25% clouds, this with 50% clouds, and this with 75% clouds. And then you can see the degree of polarization with a rainbow because of the clouds. This peak here in the UV blue is because of Rayleigh scattering. This variation, this band, is actually because he did not use one pattern of clouds, but 300 something patterns of clouds, because the clouds can be different positions on the disk. So this band, this fake band, that indicates the effect of different cloud patterns. But what is very interesting is that this polarization in different colors, the lines cross each other at a certain phase angle. And this is unique for a planet with an ocean surface. So if the planet has a dry surface, you do not see this in our model calculations. And the location of this crossing depends on the amount of clouds. So if you have lots of clouds, it really shifts to very large phase angles. This is a bit typical for the Earth. If you have less clouds, might be around 120 degrees. So yeah, this has not actually been measured again, but a little bit it has been measured, not from space, but from Earthshine measurements. So with Earthshine measurements, you do measurements of the night side on the moon. So this is from the VLT actually. Here you see the VLT. I don't know, this might be Venus actually. So here you can see the moon. So the light part is the day part of the moon, and the darker part is the night side of the moon. So if you would be sitting on the moon, it would be night, but you would have a huge Earth in the sky, and you would have Earthshine. And that's why you can also see here patterns on the lunar surface, because it is not completely dark, because the Earth illuminates the night side of the moon. So that is Earthshine. So people have done lots of these measurements of the Earthshine in spectra, in flux, because it is basically a very bad mirror for the Earth, what the Earth looks like from space. But it's very bad because it is very rough, the surface. And so especially for polarization, it is very tricky, because the lunar surface depolarizes the light of the Earth a lot. And we don't know how much it depolarizes the light, because you cannot measure that from the Earth, because then you have to know the degree of polarization of the Earth and then look at the Earthshine. So we don't know how much the moon depolarizes the light. So these are observations by Michael Sturzik from ESO, and I was also involved in these observations. It was very interesting, because the VLT cannot follow the moon, because you are not supposed to look at the moon with the VLT. So that had to be done by hand. So very interesting. And here you can see measurements for different colors of the degree of polarization. There's no rainbow, because that phase angle cannot be measured for the Earthshine from the Earth. And you can see that these curves appear to cross each other. So yeah, there is a hint of this crossing in the polarization. So we have actually put in a new proposal to find these oceans and to do these measurements somewhat better. There are lots of problems with Earthshine. As I mentioned, we don't know how the moon depolarizes the light. You cannot actually monitor the effect of the rotation of the Earth, and you cannot measure all the phase angles. So, but still you can do something. So with the new proposal that Michael submitted 2 weeks ago or 3 weeks ago, we also want to look at spectra, because these are new computations. This is polarization for dry planets and different cloud coverages. This is polarization for cloudy planets. And when the glint is covered by clouds, so like this, the polarization looks the same as for a dry planet. But when the glint is uncovered, then you should see features like this. So that is something we try to measure if this proposal is accepted. So we want to observe the Earthshine long enough for the glint on the oceans on either side of Chile to be uncovered. So maybe depends on whether we have observation in the morning or in the evening part of the night. That depends which part of the ocean you will see. So, well, who knows? Maybe we get this and might detect the oceans on the Earth. So we do not have good measurements of the polarization of the Earth from a large distance. So here you can see a flux observation of the Earth, the famous pale blue dot, and the Earth is actually over here. really pale. This is all scattered light in the instrument. So this was from 6 billion kilometers away. This is the Earth seen from an orbit around the moon, not in polarization. So we want to have really good observations of the Earth from a distance, because then you can validate your codes that simulate fluxes and polarization. You can test retrieval algorithms so that you know if we observe an exoplanet and we derive that it has 50% clouds and a huge continent, is that really the case? Where you can really test it with the Earth. And that, of course, is important for the design of these future huge observatories. They also cost a lot of money. So you want to make sure that they can actually measure all the things that are there to measure, that will help us to characterize these planets. So that's what we have been working on to get such an instrument in space. So because then you can see here, you can see the Earth in different phases, in flux and polarization. And here are some, again, computations, the total flux. This is basically as a function of the phase angle using real data of clouds and also wind speeds over a year with MODIS data in different colors with a rainbow here. And in polarized flux in different colors and in degree of polarization. So we want to measure this and to check this to see whether this is for real. And from afar, you can see the Earth as a whole with the same illumination as you will get for an exoplanet. Well, of course, depending on the inclination angle of the exoplanet's orbit. This is a simulation of what the Earth would look like from the lunar surface. So if you would have an instrument on a lunar lander, you'll be able to see the Earth rotate. You see different phases. If you are long enough, there's a little jump in the thing. If you are on the moon long enough, you can see seasons, and you can see the glint over here. So so that's what we want to measure. And that's indeed why we have developed this loop instrument, Lunar Observatory for Unresolved Polarimetry of Earth. That is an instrument that should go on the lunar lander. The nice thing is on the moon, of course, on the good side of the moon, that the Earth is in the sky all the time, approximately in the same location. There is some variation here because of the orbit of the moon and also of a bit of vibration. So that is interesting. The moon is actually not ideal. It is very nice, of course, nice to go to the moon, because you have the lunar night. You want to measure throughout the lunar night, but there is no sun, and so there are no solar panels that you can use, and so there will not be no power. So that's why we actually think it's better to go in space, and so that's why we submitted this SELFIE proposal. So Van Snick from Leiden has thought about what these letters stand for. We are not sure yet, but this is a proposal for a fast mission. So the call was in December, the deadline was in February, and maybe this week or next week we will hear whether we can continue to the next round. So this is a plan to observe the Earth as an exoplanet, not from the lunar surface, but from L1, between the Earth and the Moon. So L1 is the distance from the Earth, about 320,000 kilometers, where the gravity is more or less balanced, and so you can put a spacecraft there. It is not stable, that location, so if you put a spacecraft there, it will drift away, so you have to do some station keeping, but you have the whole Earth in view. It is small enough to capture as a whole. You can see the daily rotation, the phases, the seasons, because you have power all the time, so you can stay there for 2 years. That's the length of the fast mission, according to ESA. You can calibrate your instrumentation by looking at the moon. The moon is used a lot for Earth observation missions as a calibrator. And there are lots of data available in which the moon is observed from the Earth for calibration, also in polarization. There is no dust, And of course, it's very nice for public outreach because people will know when you see the moon that the instrument is over there. So, yeah, so L1 is 323,000 kilometers away from the Earth, from the center of the Earth. It's a little bit inclined, which is nice because then you can also see the polar regions of the Earth. So this is almost my last slide, actually. So the main instrument will be what we call a hyperspectral polarimetric imager. This is the instrument, HyperScout, that is already in space. So it was launched the first time in 2018. This HyperScout does not measure polarization, but we have adapted it. So this is a HyperScout with a detector over here. And it has a linear variable filter that is part of HyperScout. So that makes sure that there is a range of wavelengths on the detector. And we have expanded it with a patterned liquid crystal and a polarizer and a micro lens array. And what you get then looks like this. So this is your detector. And you get all these little dots on your detector. And every dot is an Earth. And on the vertical axis here is the color from 400 to 1000 nanometers. And on the horizontal axis, because of the patterned crystal, there are all the directions of linear polarization. So the different dots have different colors and different directions of polarization. There is some redundancy, so that's nice. And so, yeah, so this is a simulation of what a detector should measure. Yeah, so to summarize, so polarimetry provides unique information on planets and exoplanets, on clouds and surfaces that is not available in total fluxes. So it's really important to include it. It is independent of lots of things, distances, planet sizes, many instrumental effects, and the Earth atmosphere. For most solar system bodies, you should go to space because you need the phase angles, that is best. And nowadays there are very small polarimeters that do not have rotating filter wheels and these kinds of things, so that they are completely robust without any moving parts and very small, and they can be very accurate. And so we hope to have small missions like Loop on a lunar lander, piggybacking on a lunar lander, not by itself, and maybe SELFIE to get test data. And so that will help us to identify habitable exoplanets in the future. So if we are allowed to put in a phase 2 proposal, there will also be a camera on the orbiter to make a picture of the Earth spatially resolved. So you know what it looks like, but mostly also for public outreach. And there is also space for all instruments, like maybe an infrared camera, passive, magnetometer, maybe something else. So that is something we will investigate in the coming weeks, months. So thank you.
Thank you so much, Daphne. This was just amazing. I keep being enchanted by polarimetry, although it's so difficult.
Yeah, it's not so difficult.
Oh, okay. Well, then for you, it's not difficult.
No.
Okay.
Yeah.
So let me just quickly check whom we have as a question. I would suggest we keep this round of question very short. So if I call someone to for asking the question, keep it short, because then we can come back and discuss a little further. Peter, you are still recording, right? Do you want to stop the recording?
Okay, I can.